Hello everyone. This is our second lecture for Chapter 10, Two Independent Samples T Statistic. In this video lecture, we will continue discussing the hypothesis testing steps for an independent samples t-test. We already discussed this steps 1 and 2, so now we will start with step 3, calculate the test statistic. The test statistic for the independent samples design has the same structure as the one sample t introduced in Chapter 9, where t is equal to the sample statistic minus the hypothesized population parameter divided by estimated standard error. However, in the independent samples situation, all components of the t formula are doubled. There are 2 sample means, 2 population means, and 2 sources of error contributing to the standard error in the denominator. In the formula for an independent samples t-test, we subtract the mean difference between the sample means, M1 minus M2, from the mean difference stated in the null, mu1 minus mu2, which is always equal to 0. So this is always equal to 0. This simplifies our numerator so that we just have to calculate the mean difference between the 2 sample means. We then divide this difference by the combined standard error in both samples, called the estimated standard error of the mean difference. The estimated standard error of the mean difference measures the average distance between sample mean differences M1 minus M2 and the population mean differences mu1 minus mu2. How much difference should we expect between 2 sample means if the null hypothesis is true? The formula on this slide can only be used if sample size n for group 1 is equal to sample size n for group 2. N1 is equal to N2. In this case, we do not need to weight each sample variance by its respective degrees of freedom. We can go straight to calculating an estimated standard error. We divide each sample variance, S squared, by its respective sample size n, add the 2 results together, and then take the square root. For unequal sample sizes, to find estimated standard error of the mean difference in the denominator of our t statistic, we need to calculate S squared p, which is pooled sample variance. Remember that S squared is sample variance. Adding a small p in the subscript makes this pooled sample variance. A pooled sample variance is the mean sample variance for 2 samples. When the sample sizes are unequal, the variance is a weighted mean so that the pooled sample variance is weighted toward the sample mean calculated for the larger sample size. The larger n is, the better the estimate of sample variance will be. The formula for calculating sample variance when the sample size is different in each group is pooled sample variance equals sum of squares from sample 1 plus sum of squares from sample 2 divided by degrees of freedom from sample 1 plus degrees of freedom from sample 2. The second formula is equivalent. It's the same. Pooled variance equals variance times degrees of freedom from sample 1 plus variance times degrees of freedom from sample 2 divided by degrees of freedom from sample 1 plus degrees of freedom from sample 2. The pooled variance formula you use will depend on what information will be given to you in the problem. Pooled sample variance is not estimated standard error. We are not done yet for the t statistic denominator. Now that we have pooled sample variance, we can finally calculate estimated standard error of the mean difference. We substitute pooled variance and sample size in the formula. So estimated error, we divide pooled variance, S squared P, by each sample size. Add the two results together and then take the square root. We can now calculate the test statistic for independent samples t-test. We take the sample mean difference and divide by the estimated standard error of the difference. This gives us the obtained or calculated t-statistic. Step 4, make a decision. To decide whether to reject or fail to reject the null hypothesis, we compare the obtained or calculated t-statistic to the t-critical value. If we reject the null hypothesis, we must provide a measure of effect size. Effect size for independent samples t is measured in the same way that we measured effect size for one sample t in Chapter 9. Specifically, you can calculate an estimate of Cohen's d, or you can calculate r squared to get the percentage of variability explained by the independent variable or by the treatment effect. When estimated Cohen's d is used with independent samples t-tests, we place the difference between two sample means in the numerator and the pooled sample standard deviation, or square root of the pooled sample variance in the denominator. Another measure of effect size is the proportion of variance, or variability in a dependent variable that's explained by the independent variable or the treatment. Percentage of variability is calculated using the same formula for both one sample and independent samples t-test. Effect size can also be calculated using confidence intervals. Same as we did for one sample t-tests in Chapter 9, we find the interval estimate reported as a confidence interval and state it within a given level of confidence, which is the likelihood that an interval contains an unknown population mean. Using sample mean difference, we calculate confidence interval by adding and subtracting a margin of error, which is obtained by multiplying t-critical value and estimated standard error. One last slide for independent samples t-tests. The assumptions that must be met in order for us to conduct an independent samples hypothesis test are the same as the assumptions for a one sample hypothesis test plus one more. The three same assumptions are random sampling, independence of observations, and normal population distribution. The new assumption is that the two populations must have equal variances. This is called the assumption of homogeneity of variance. In order for us to be confident in our results, the populations we are sampling from must have equal variability. This assumption is usually satisfied when the larger sample variance is not greater than 2 times the smaller. Larger variance divided by smaller variance has to be less than 2. I will post a video to demonstrate how to conduct an independent samples hypothesis test, both with equal sample size and unequal sample sizes.